Hello, everybody. So we are starting the webinar now. Welcome to this Society of Floating Solutions Singapore webinar. I'm Stefan Hübner from NUS, the National University of Singapore, and I'm also the president of the society and will moderate today's event. The topic of today's talk is floating city digital twins, the future of coastal resilience and sustainability. And we are very honored to welcome today's presenter, Wenhui Zhao from McNeese State University, where he is an assistant professor in the Department of Engineering and Computer Science. He received his bachelor's and PhD degrees in civil engineering from National Taiwan University, and prior to his current appointment, he conducted postdoctoral research at the University of Texas at Austin and at Louisiana State University. He also gained professional experience in the marine and coastal engineering sector at Kauai, North America. Today's webinar topic is very important as climate change accelerates sea level rise and intensifies coastal hazards. Advanced floating city designs have been proposed to create more solutions for resilient and sustainable urban living. Think of UN Habitat and the Busan project, or Oxagon as part of NEOM in Saudi Arabia, or the Maldives floating city or Square floating city, and so on. In this webinar, we will hear about the development of a next generation digital twin technology that integrates real world data with a virtual floating city to optimize design, operation, and maintenance. Wenhui will also showcase a pilot digital twin for a conceptual floating city in San Francisco Bay. And now a few administrative remarks before we start with the presentation. The talk will be about 30 to 40 minutes and then followed by the Q&A session. But if you have any really immediate questions, it will also be okay to ask them during the presentation. Later, please feel free to post your questions in the Q&A box, which I then read out on your behalf, or use the Zoom raise hand function. In that case, I will call you up so you can ask your question yourself. Moreover, we will be recording the talk, as you noticed when you joined, and as you can see here also on the screen. And we may upload it to our YouTube page. So by being here, you give consent to that. Wenhui, we are very happy and grateful to have you with us today. So please, the floor is yours.
Thank you. Thank you very much. Thank you, Dr. Stephen, for having me today, and thank you for the introduction. So good evening and good morning to Singapore. My name is Wen Huai. I'm an assistant professor at civil engineering and at the McNeese State University. And it's my pleasure to present my research about the floating city digital twins and the future of coastal resilience and the sustainability. And thanks, Taiyan, to inviting me that we met in the OMA conference this year. And I realized that there's actually a group of people in the other end of the earth really care about this idea, the big picture of a floating city because of there are different concerns in different countries, and I just realized that how valuable of my research is, and that's I really appreciate that, and also this opportunity. So I'll go ahead and start it. Today's topic. I'd like to start with our vision first. And let me use the laser point. Okay, so our vision is to build a resilient and sustainable coastal communities overall, and therefore we have to address some challenges like sea level rise. So this is flood statistics data about the the damage and the flood depth. So some area like New Orleans, and half of the structure will be gone, even with just 1 foot flood depth. It's pretty crazy. And also we have compound flooding in a coastal transition area, and this combined effect of the storm surge. Uh, High tide, heavy rains, and river discharge will lead to flooding more severe than ever. Okay, and we have a coastal ecosystem degradation, which means that we have lost a significant land use potential due to intense mismanagement or human use, and it changed the region's potential over the past decades. And therefore, we're looking for some sustainable solutions. Like first, there's a waterfront parks, which means they are recreational space that are intentionally designed to be flooded with minimal damage during the storm events. And also, we want to protect our nature shoreline, which can reduce the wave impact and capture tremendous amount of carbon dioxide. And also, we want renewable energy. The coastal area has great potential in harnessing various kind of clean energy like wind, wave, current, solar energy. And therefore, we proposed a strategic plan. This is called the Floating City, and which focus on the sustainable living with water, and it includes all kinds of human necessity like water, food, energy, transportation, and we must have a productive infrastructure that is designed for extended service life, either it is nature-based or structure-based. And we want our floating city to be adaptive, so that it allows the system to adjust itself according to the changing environment. And we know it's a broad topic, but some module has already been proposed, tested, or even very mature in practice. For example, this is the floating agriculture. The floating fisher cage has been widely applied for a long time. Floating PV farm recently has been deployed in many places, especially in Asia. And Norway just aimed at a 200 megawatt floating nuclear power plant. And Korea also has a vision building a floating city. So, however, the coastal environments are more complex than the inland system. And therefore, my question is that how can we turn this complexity into practical solutions? So, my solutions is to leverage the digital twin technology. So the term digital twin technology is originally coined in the early 2000, but the first practical application can be tracked to the Apollo program. And another good example is the Apple Watch. And this device is, I don't have an Apple Watch, but I know that this device is collecting data and identify our health condition through their numerical models. And more importantly, these data are not generic bad data, but a personalized data that continuously update as my physical state changes. So it's like I have a twin in my watch, and it's digital, and that's why I call it digital twin. So according to this example, the key feature of the digital twins are first, the data collected from the system and the model that encoded the governing law of the system. And this process to combine these two components together is called the data assimilation. And therefore, we can predict that the system's behavior to provide a recommendation future further actions. So similarly, we can build a floating city digital twin through the 4M framework. That's a name that I make up. So 4M is not 4 million, and it's now also not another company like 3M. So they are first of high fidelity air water flow models. So it stands for multi-phase. And secondly, it has multi-body dynamic solver, so it's multi-degree of freedom. And it can do fluid structure interaction simulation, so it's multi-scale. And then finally, it has physics-based reduced order models. So it's multi-fidelity. So I will explain this idea later, so that you kind of understand how we can apply the 4M framework. And for the reduced order model, I like to make a special explanation is that it's known as a surrogate model, and it's built to simplify the higher order model so that we can reduce the computational cost or accelerate the computational results. But however, these reduced order model are usually system specific, which means it is tailored to capture the dominant dynamics of each application. And therefore, I will present our ROMs separately in the following three pilot, like proof of concept studies. And meanwhile, I explain how I apply the 4M framework to verify the digital twins. And finally, I will show you some conclusion and future research directions. Okay, so let's jump to the 4M framework. The first module is focused on the high fidelity and the low order flow models, and which this forms a backbone, a physics backbone of our numerical wave tank. And we have three models to handle different scenarios from the high order to the low order. We have multi-phase Navier-Stokes flow model, potential flow model, and the shallow water model. So, for example, this is a tsunami overtopping the seawall solved by the two-phase Navier-Stokes model, and this is a uh, wave transformation over a submerged bar, solved by potential flow, and this is a wave diffraction over island, solved by the shallow water flow model. And this module will build upon the efficient finite element and boundary element methods to achieve scalable parallel performance, and they are well validated. On the second module is important because it's important how we can reconstruct the real world environment in the numerical models, which is called the data assimilation. And here, this is the case that I show is about the oceanography data, which is, for example, the wave field, the wave height, the wave period. Um, so say if we got the wave data from a physical buoy and we want to replicate the wave condition in our numerical wave tank, so we will apply the window method and the relaxation zone method. So the window method means that as we extract the wave spectrum from the real wave time series, and the amplitude of each frequency components determines the amplitude of the predictive wave elevation. And then we can establish the relaxation zone. Sometimes we call it a numerical wave maker. And we can, so in the relaxation zone, we add an additional term in the Navier-Stokes equation. And so we can slowly build up the wave velocity to reach the required wave field. So this picture shows that if the wave is highly random, and then we need a more frequency component to describe the wave. And because the accuracy of the spectrum is related to the duration of the time series, so we have to make sure the recorder is long enough. And the next module is the hydrodynamic analysis in fluid structural interaction, where we focus on the pressure and force applied on the surface of a submersible structure. We've developed a pretty cool method called a cut fin, cut finite element method. The term cut means that we don't generate the mesh that is conform to the structural surface like a traditional finite element methods. but we build a background mesh first, okay, and then cut out the mesh where you put your structure. And this is extremely helpful when you are dealing with a structure with a complex geometry because you get to simplify the mesh generation. And additionally, we can avoid excessive work, remeshing work when a frequent remeshing is required, like the large free surface deformation and the moving boundaries. Okay, and this is an example of showing you that the advantage of coughing in reducing mesh work because you can see that how the mesh is directly cut into different sizes. And however, because you cut the mesh, and sometimes you get a very tiny mesh, right, like this, and it's better for numerical accuracy and stability. So we need an extra numerical treatment to fix that. For example, the Nietzsche's method can enforce the boundary condition in the average sense. Okay, and rather than directly fixing this value, it modify the weak form by adding a boundary integrals, and this terms ensure the stable solution, especially important for full structural interaction, where the interface is moving, but the strong enforcement for the boundary condition is usually impractical. And in order to get integral across the interface, we define an equivalent polynomial for the Heaviside function. Okay, this is to capture the interface of the fluid, solid, or air-water interface. So rather, so we don't just directly integrate the discontinuous Heaviside function. The polynomial behaves as the same as the true Heaviside function in a weak sense. Okay, so because the equivalent polynomial is a second order function, so that's why we call it a high order coefficient. Usually it is a first order function. Um, so the next module is the dynamics of the multi-degree of freedom systems in fluid structure interaction. And it's important because most of the coastal and the marine structure are dynamic systems. So this module creates an interface that exchange variables between the CFD and the structure dynamics solvers. And sometimes the CFD and structure dynamics solver usually will give different solutions. For example, the displacement on the interface are not compatible, or the force on the interface is not in equilibrium. And this is because we need the structure's motion to be given as a boundary condition, but the structural motion is not known until you know the hydrodynamic force. So, and therefore we need to use a strong coupled iterative scheme, okay, to enforce the conversion of the kinematic and the dynamic conditions at a fluid solid interface. And when we get the pressure and the stress at the fluid-solid interface, it's pretty simple to solve the dynamics of the MDOF system. Usually, because the time marching step is usually stable. Okay, so simple finite the time difference scheme is available. And therefore, we've done some experiment like validation about the elastic deck gate in a dam break problem. So this elastic gate is actually modeled by multiple components that link together.
All right, so I can show you some of the proof of concept study that will be applied in the floating city digital twin. So the first study is the natural shoreline protection, specifically the mangrove forest as a coastal defense. So our goal is to establish a numerical framework to estimate the drag and hydrostatic damping of a mangrove forest and then further evaluate the resilient performance of natural shorelines. So this is an example of a wave propagation over a mangrove forest. So this experiment was done by the Oregon State University, where they built a artificial mangrove forest with a bunch of PVC pipes in their waveform. And they measure the wave attenuation induced by different porosity settings, which is mangrove density under different wave conditions. So this is a result obtained using the two-phase Navier-Stokes solver with a caffeine. And you can see the vorticity distribution on the submerged surface, which means that we can analyze the wave damping during the fluid structure interaction. Another challenge we faced was the waveform is actually quite large. So the mangrove forest is 60 feet long and 12 feet wide, and there's a lot of fake tree model inside. So it's impossible for us to run the full-scale simulation, which will eat up all our HPC quota. So we need a reduced order model of the mangrove forest. So note that the ROM was derived based on a physical simplification. So we assume the flow in the mangrove forest is a Darcy's Forge-Hammer flow region, and therefore we add a quadratic term in the momentum equation. This term is a sink, so it provides numerical damping to dissipate the wave energy. And now our problem becomes, what are the drag coefficient alpha and beta? So to answer that, we conduct a regression analysis on the drag. Okay, we first divided the tree model into several layers because each layer at a different height has different porosity, and in theory they will bring different damping effect. And then we input a uniform flow and calculate the drag also by using caffeine. So we can establish the drag velocity relationship, and then we approximate this curve by a quadratic function. And therefore we can get the drag coefficient at the different heights as shown. So when the Darcy's Forge-Hammer assumption is applied, what we actually do is to model the mangrove forest as a porous media zone. And therefore, you can see in the modified numerical wave tank, the mangrove forest is replaced by several layers of porous media with different drag coefficients. This area provides the same damping effect as the caffeine model. And one thing to keep in mind is that the ROM only includes the energy dissipation, and so it can not simulate the wave reflection and diffraction, so we have to correct the boundary condition of the porous media. This is quite important for 3D simulation, so it will be studied in the future. The second POC study is about the structural vibration control in water-based system. So we've improved the stability of the floating structure through a passive damper using a passive damping made entirely out of water. It is also known as a tuned liquid damper. So as the tuned liquid damper is installed, you can see how much difference between the motions of the uncontrolled and the control platform. And if you look closely, you will see that the sloshing fluid inside is creating an out-of-phase force that can cancel the wave force. And the wave energy is then transferred to the sloshing fluid and then dissipated through the sloshing damping. And similarly, the water tank can also serve as a floating breakwater to protect the coastal structure. So in this simulation, the transmitted wave behind the floater vanishes because the wave energy is also dissipated by the water tank. And we can simulate the motion of the mooring line, where each catenary line is represented by a series of bar elements, and then we can get the attention for further mooring analysis. And we have also done another experiment to verify the design of the tuned liquid damper. So this is the tuned liquid damper mounted on a pendulum subject to ground excitations. and we can always find the optimal dimensions and the associated material property of the porous media inside the tank. And therefore, the tune liquid damper will satisfy the tuning frequency and the optimal damping ratio given by the tune mass damper design theory. And therefore, the overall frequency response of the pendulum can be minimized as shown in this figure. So from this video, you can see how the tune liquid damper reduces the vibration of a pendulum, and the mechanism of the energy transfer and the dissipation is the same as the previous example. So based on the other research we've done before, although the free surface deformation can be large, the nonlinear solution force comes from the convective term is actually somewhat insignificant. Okay, so therefore it's negligible, so that we can build also build a room for a solution fluid. So I'll skip the derivation, but I can give you a very straightforward derivation. So the left-hand side equation is the free surface motion equation derived from the linear wave theory, and the right-hand side equation is the motion equation of the mechanical system. So you see how similar they are, and both are second-order ODE, and therefore we can transform a water tank into a multi-degree of freedom system, and their dynamic response are equivalent. And each mass represents a solution mode, but since the fundamental mode is the most important, and we can ignore the high frequency mode, and finally we have a super simple model. Okay, so the solution fluid in the tank can be represented by a mass with a spring and a dashpot attached to it. It's hard to believe, right? And we can characterize the nonlinear damping. So this ROM can be quite accurate in solving hydrodynamic effect in fluid structure interaction. And more importantly, you reduce the degree of freedom of the free surface motion, making the computation super easy and fast. So with all the data assimilation skills and the computational flow model and the fluid structure interaction solver, we're ready for a pilot floating city digital twins. And this is a Berkeley Marina in the northern California. And there's a renovation project to reopen the pier for recreational use. So the original design is to build a ship pile breakwater to create a sheltered water area for ship berthing. But it's also the perfect spot for some pilot testing. And first of all, we gotta have the wave data. The data is collected from the city IP buoys 142 and 41, these two yellow dots right here. And one outside the Golden Gate, another one inside the bay. And however, they are miles away from the site. If we directly use this data, our numerical domain will be extremely huge. We can't afford that. So that we go with the plan B, that we use a commercial software, Mike 21, to simulate the wave condition near the Berkeley Marina. And then we assume the result from the Mike 21 are real wave data. So in fact, there are no buoys right there, but we pretend that Mike 21 is my buoy. And therefore, my virtual buoy defines the wave inputs such as wave height, peak period, and the wave directions. So the location of the buoy is also a key question for successful digital twin deployment. So for example, the long period wave propagates faster, so we need to put the buoy at a far distance to capture that. Otherwise, by the time we obtain the data, the wave will have already hit the structure. So on the other hand, we cannot put the buoy too far because that will result in an oversized numerical domain. So this figure shows the available distance between the buoy and the structure under different wave conditions to guide us how to design. And here we have our first floating city digital twin. We have a numerical wave maker that can reconstruct the real waves and porous breakwater that can protect our floating house, and the adjustable pile supported floating platform for house installation, and a water tank that can serve as a floating breakwater or a drinking water reservoir. That's beautiful. So this model demonstrates the digital twins potential to monitor and optimize structure design, and in the future to interact with the user in real time. And next, I'm going to show you some of the ongoing and future research. So the first ongoing research is the structured data assimilation. One advantage of the CUP film is it can take a fieldwork result. So for example, this is the LiDAR point cloud of a real mango tree. And this image was taken in Florida by the student. We did some post-processing to clean up the tree model and then import that into our numerical wave tank to run the wave structure in simulation. And similarly, we can measure the material properties such as stiffness to solve the oscillation motion of the structure in waves. So if we monitor the characteristic change, we can adjust the numerical setting and enable an active control feature. And the second ongoing research is to improve the resilience of floating city under extreme climate conditions. So for example, the system's response, what is the system's response under wind wave current coupling effect? And we already done some hydro and aerodynamics analysis on floating solar panels. So our next step is to enable more comprehensive environmental reconstruction to improve the digital twin capability. And more importantly, because the traditional CFD is restricted to statistical analysis under varying meteorologic conditions and physical settings, so we have to quantify the uncertainty in the system. And this is also provides another way to develop the reduced order model of the floating structure. So in the final slides, I've prepared some key takeaway and our future research direction. We presented how we implemented the 4M solver with data assimilation to build a floating city digital twin. And in the future, we will focus on data-driven surrogate models, which will not only reduce the computational cost, but also enable statistical analysis. And we will also need a lab scale and fieldwork experimental result to validate the digital twin. And also we want our digital twin to be able to respond in real time and interact with the user. For example, the active control and the virtual reality. And the final point is about the interdisciplinary collaboration. This initiative is not only an engineering problem, but also involves the urban planning, policy, economics, and other fields. And last but not least, I hope we can transfer the future engineering practices through solid scientific approaches and build resilient and sustainable coastal communities. Finally, I'd like to acknowledge my former colleagues and their contributions. My research has received funding from the U.S. Army ERDEC, LSU IEI, National Science Council of Taiwan, and a co-funding in Denmark. So this is the end of my presentation, and thank you very much for having me. Please feel free to reach out, and I'm ready to take any questions. Thank you.
Yeah, thank you. Thank you very much for this very interesting talk. People can feel free to react. I mean, you see on the screen the clapping hands and so on. So before we come to the Q&A, let me make a few short announcements. Yeah, I would like to mention that our Society of Floating Solutions Singapore is a society that has international membership, and we are always interested in discussing innovative floating structures to solve various environmental, social, economic, and other problems. So feel free to go to our social media, our YouTube, our LinkedIn, and so on, our website, which you can find in the chat, or you can just search for them. And also, if you are then interested, please consider joining us as a member. Student membership is free. The membership not only supports our activities, but also gives you a discount on our activities. Recently, last week, we, for example, did a site visit to the Chirata floating solar farm. And then also earlier this month, we had our World Conference on Floating Solutions. And I also want to mention that the next World Conference on Floating Solutions, the sixth one, will take place from 21st to 23rd of September 2026. So in about 1 year in Singapore, and registration and paper submission will start in a few months. The event brings together academics, industry, and practitioners, regulators, and covers all types of floating structures and corresponding topics. So this may be something of interest to you all. Yeah, thank you very much again for the presentation. And the guests, if you have questions, please either post them in the Q&A box or in the chat, or use the raise hand function, and then I will read them out for you. And I will use my role here as the moderator also to maybe squeeze in one first question. You talked a bit about the future, but I wonder more generally, in the long run, do you see this more as an academic tool for researchers, or do you consider commercialization in case there is a stronger increase in floating city, floating settlement projects, or what are your ideas in this regard?
Yeah, that's a great question because first of all, this is a new area. So not only for digital twin, but also plotting city. The concept is also new. So before we really work on some practical project, we need some validation or maybe pilot testing. And I don't think industrial company is willing to do this at this moment unless they think um, this could bring any profit or this is very urgent in certain places. However, those components, um, as I mentioned in the very beginning, a lot of them have been tested or maybe have been put in the practice and run for operated for a long time, like the floating fisher cage, or the floating bridges, floating airport, very large floating structures. These are very mature topics. They can be a great foundation for our future design. So as long as there is a need, for example, if the Norway is going to build their small power generator on offshore or nearshore on a floating platform, I think this will kind of this initiative will grow eventually along with the time. It doesn't need to start with floating city. Maybe first thing people hear this might think about, okay, this is some houses for human residents, but actually, uh, if you this actually involves it's a broad topic, it involves the various component, and we are actually doing this, although these are new and seems that nobody touched this before, but actually as a researcher or as a company or private sectors, actually we are doing this already. We're already doing this for a long time.
Okay, thank you very much. Yeah, as mentioned, if you have questions, then please feel free to post them in the chat box or the Q&A box, or use the raise hand function. I have another quick question, if you don't mind.
No problem.
And you talked a bit about San Francisco Bay. I mean,
Yeah.
this one could use any place, I think, for yeah, as a substitute. Is there other than that there is this yeah current opportunity, any other reasons that make San Francisco Bay particularly interesting? I mean, it's located in an area with access to also very good infrastructure and so on. But is this more the convenience of possibility that is emerging there, or is this also driven by other environmental considerations, for example? Or
Yeah. Yeah, that's a great question. So, previously when I work in COE, we were working on a project in Bay Area, and that's the first reason that I choose because I get to gather uh, comprehensive data in the Bay Area, either is topography or the wave data, the wind data, the environmental data, or the structural data. So there's is actually exactly what a digital twin need. Um, to have all kinds of data and then form your digital model as comprehensive as you can. And the second reason is that Bay Area is a well sheltered area. So the wind offshore is quite large. However, not much of the wave come into the bay, and it's a good place for preliminary research because we don't need to deal with a very complex wave field at this time. But however, I think there must be some other better place um, worth studying, especially for those area that uh, is undergoing a severe threat of a sea level rise. For example, in New Orleans or in the Mississippi Delta, if we're talking about the United States. And that's it's a more urgent for them, and it can actually attract more people's attention if we put our if we test our digital twin in that area. Yeah, so it's something that we can work on together in the future.
thank you. Yeah, I was thinking in the Netherlands, it's probably also interesting in terms of both availability of data and also in terms of yeah, the climate change related risks, as well as some,
Yeah.
let's say, homemade risks
Yes.
to some previous practices there. So let me check again. Any more questions here? Use your raise hand function, or post them if you like.
Thank you.
I think yeah, this was a very comprehensive presentation with that covered many important topics and has a global applicability. So I think we have covered what people were interested in, and I also want to suggest to everybody, if you have follow-up questions or more specific questions, also just follow up via email. We can also, if we want to continue some moderated chat, if that is of interest, via email, for example. I can forward this. I can also put together an online discussion system if there's interest. So yeah, we can continue the conversation. And as mentioned, actually, there is one more question if we can squeeze this in, since we have 1, 2 more minutes left.
Sure.
From Charles, our vice president and secretary, referring to potentially, this is in the Q&A box, referring to potentially phase change of water to moisture of, let's say, a thermal power plant. Can air also be simulated in the model? So yeah, can you include?
Um,
Yeah.
yeah, yeah, I just saw the question in the Q&A box. Yeah, it's a great question. So, um, first of all, this is a two-phase model you might need to use. And secondly, I think this physics phenomena involves thermodynamics. So currently, our numerical model does not involve this process, cannot handle this process. And because we're mainly focused on civil engineering instead of chemical or mechanical. But I think if the problem would be like simpler, like it does not involve the thermodynamics, definitely yes, we can handle air, water, or air structure interaction. Like I just show you an example about um, the solar panel in under wave loading, um, and also the two-phase model for simulating the tsunami. So these are great example that shows the potential of our methods solving the multi-phase flow.
Okay, thank you very much then for answering the question. Yeah, also thank you in Charles' name. You saw the thumbs up.
Thank you.
Okay, let me check again. We can do a countdown. If you have any more pressing questions, then just raise your hand or post in chat. I can count down from 10 to 0, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, then I think we can thank the speaker again.
Thank you. Thank you very much. Thank you for having me today. Yeah. Very look forward to seeing you in the future.
Yeah, me too. And
Thank you.
there can be a number of opportunities from online to maybe in person at one of the world conferences or at some other event. So not only thank you to you, but also to our participants. and we will work on uploading the video so that people in Europe who are currently, most of them are sleeping. We had one Italian guest. Thank you for joining.
Yeah.
You can
Thank you.
watch it and follow up with you then later. Okay, so everybody have a good evening if you're in the US, or a good morning in Singapore or Asia, and we will reconvene in November or early December for our next webinar on recreational floating structures.
Thank
And
you.
if there are more events, then also please, as mentioned, consider joining our social media so that you actually stay informed. We also have our annual dinner in November. You can also find information on that on our social media. You are most welcome to join us for that event if you are in Singapore. Otherwise, as mentioned, we can have our alternative annual events at one of the world conferences. Okay, then goodbye, everybody, and stay safe. Bye bye.
Goodbye. Thank you very much. Goodbye.